Welcome to your Deep Dive Systems Briefing. Today, we're going to master piston engine fuel. Pay close attention, because what you learn here will be absolutely critical, not just in your technical interview, but more importantly, in the cockpit.
So here's our flight plan for this session. We'll start with the fundamentals of AV gas itself. Then we'll define what that ideal combustion process looks like. From there, we'll confront the big one, detonation, the engine killer. We'll make sure you can tell it apart from pre-ignition. And finally, we'll tie it all together with fuel quality and the octane rating. We're going to build this up layer by layer to give you a true command-level understanding.
Okay, first things first. We're starting with the fundamentals. Because, before we can even begin to talk about what goes wrong, you have to master the fuel itself. Okay, this table right here, you need to know this stuff cold. No excuses. The key identifiers, your first clue, are the colors. AV gas 100 LL is blue, 100 is green, and 80 is red. I want you to think of these colors as your absolute first line of defense against a catastrophic misfueling event. And also take a look at the lead content. It's that lead. Even the low lead in 100 LL, that's a critical ingredient for getting that high performance number and fighting off detonation.
All right, let's talk about a really crucial property, volatility. This is basically how easily the fuel turns from a liquid into a vapor. You need this so it can mix properly with air. But there's a huge operational catch. As you climb, the air pressure drops. And what does that mean for you? It means the fuel literally starts to boil at a lower temperature. We call this low-pressure boiling, and it's a big deal because this is what can lead to vapor lock in your fuel lines, and that's a problem you do not want at altitude.
Okay, so now that we know our fuel, let's establish our baseline. What does normal actually look like inside that engine? This is what you want happening thousands of times every minute. And let's be crystal clear, this is a controlled burn, a very, very rapid fire, but it is not an explosion.
And this image perfectly illustrates that ideal sequence. It all gets kick-started when the spark plug fires. That's our normal ignition. From that point, a nice even flame front spreads out steadily across the chamber. This creates a smooth, powerful pressure rise, a firm push on the piston that sends power down to the crankshaft. And this whole event has to wrap up at the perfect moment, just after the piston passes top dead center.
So how fast are we talking? We're looking at a normal flame speed of about 60 to 80 feet per second. That's fast, for sure, but it's completely controlled. It's the perfect speed to harness that energy effectively. Now, lock that number away in your head, 60 to 80 feet per second. Trust me, we're going to come back to it and compare it to something a lot more violent.
Now, to keep this perfect burn happening across all your power settings, from idle to full takeoff power, the ignition timing has to be smart. It has to vary. Take a look at the diagram. At higher RPM, the engine is turning over much faster, but the speed of that flame front stays about the same. So to make sure we get that peak pressure at the right time, we have to give the flame a little head start. We ignite the charge earlier, we advance the timing.
All right, now we need to talk about the dark side. We are going to confront the single most dangerous phenomenon in piston engine operations. I'm talking about detonation. This is not your friend. This is an engine killer, plain and simple. If you understand this, you understand the fundamental thing that can go wrong.
So what is the fundamental difference here? I want you to picture this. Normal combustion, that's a powerful sustained push on the piston. Detonation, that is a violent instantaneous hammer blow. See the difference? One is controlled power, the other is pure uncontrolled destruction.
And this diagram shows you exactly how that hammer blow happens. It all starts normally. The spark plug fires, the flame front starts moving. But as that flame front travels, it's squeezing and heating up the leftover fuel and air ahead of it. We call this the end gas. If that end gas gets too hot and too compressed before the flame gets to it, bam! It just explodes on its own. It auto-ignites, creating a massive pressure spike that slams into the piston.
And remember that number I told you to hold on to? That 60 to 80 feet per second for a normal burn? Well, during detonation, we're talking about 1,000 feet per second. That's not a flame front anymore. That is a shockwave. It's an explosion. And that is the source of that audible pinging or knocking you might hear just before things go catastrophically wrong. So what causes this nightmare scenario? Well, these are the things that are on you as the pilot to manage. Running the mixture too lean, letting your cylinder head temps get too high, using carb heat at the wrong time, all of these things can push that end gas over the edge.
But that last one on the list, using the wrong grade of fuel, that's probably the most direct path to detonation, and it leads us perfectly into our final topic.
But wait, before we jump to fuel quality, there's a common point of confusion we have to clear up right now. It is absolutely critical that you can differentiate between detonation and pre-ignition. They are not the same thing, and any good interviewer will nail you on this if you mix them up. So what's the bottom line? It's all about timing relative to when the spark plug fires. Pre-ignition is simple. Pre means before. The fuel-air mix lights off from a hot spot, like a glowing piece of carbon, before the spark plug even gets a chance to do its job. Detonation, as we just saw, is that end gas explosion that happens after the spark plug is already fired and the normal combustion process has begun. They're fundamentally different events.
Okay, so with that cleared up, how do we defend against detonation? Well, our primary weapon in this fight is using fuel of the correct quality. And that brings us to the single most important property of aviation gasoline, the octane rating.
Don't let the term octane rating intimidate you. It's a really simple concept. All it is a measure of the fuel's ability to resist detonation. Think of it as its stability rating. A higher number means the fuel can handle more heat and more pressure before it gives up and explodes. It's crucial to know this isn't a measure of how much energy is in the fuel, but rather its ability to release that energy in a controlled way.
Now, you might see older fuel grades listed with two numbers, something like 100/130. What's that all about? Well, it just tells you how the fuel performs in different conditions. The first, lower number, is its rating for lean cruise power settings. The second, higher number, is its performance rating under rich mixture, full power conditions like on takeoff. And why is it higher? Because that extra fuel in a rich mixture actually has a cooling effect, which helps fight off detonation.
So at the end of the day, why do we even care about high-octane fuel? Because it's the key that unlocks engine performance. Because the fuel can resist detonation, engineers can design engines with higher compression ratios, they can slap on superchargers and turbochargers to cram more air in, and the result of all that is a massive increase in power, all without the engine tearing itself apart.
All right, let's put you in the hot seat. This is where all this theory meets reality. Imagine you're in your technical interview, and the examiner leans forward and asks you this. Your POH requires 100 LL. You divert to a remote field that only has AV gas 80. Can you use it? Explain your reasoning.
Okay, how do you answer that? Your response needs to be immediate, decisive, and grounded in safety and first principles. No hesitation. You start with the rule, the what. No, sir. Using a lower than required octane fuel is prohibited. Full stop. Then you deliver the why, using everything we've just discussed. You explain that the engine was designed for the high anti-knock properties of 100 LL. Using AVS 80, which has a much lower resistance to detonation, means that fuel will auto-ignite under the engine's normal operating pressures. This will lead to catastrophic detonation and almost certainly engine failure. That is the answer of a future captain.